In this lesson, we are going to learn about the emission spectrum of hydrogen. We know, as per the Bohr model, the electrons can exist in only certain energy levels. The ground state is n equal to 1. That is known as K shell. So this is ground state. N equal to 2 refers to the first excited state. N equal to 3 refers to the second excited state, and so on. Now these are known as K, L, M, N, O, P, Q shells. You may wonder why we start with K, why not with A? Actually, when these were given names, initially somebody called this level A, B, C, D, and so on. Then something below that was discovered. So then he cannot give it any name. So next time he decided, I'll call the starting one K. If something below that is discovered, then we'll call it J, and so on. Actually, I just modified the story a little bit. That was in relation to X-rays. But that is the reason why I start with K. K shell is the ground state. L shell is the first excited state. And then it goes on. N is called principal quantum number. When an electron moves to an excited state, it remains there only for 10 to the power minus 8 seconds. And then jumps back. And jumps back, it emits a radiation having energy equal to the energy difference between the levels. So the electron jumps from here to here. We'll get a particular wavelength of radiation. That is K alpha. This is called K alpha radiation. Jumping from second level to ground state, that is K beta. These lines lie in the ultraviolet region of the electromagnetic spectrum, and they are called Lyman series. So Lyman series is in the UV region, right? Now just the second level. Then we have got L alpha, L beta, L gamma. These lie in the visible region of the electromagnetic spectrum. And that's why they discovered first. Some person gave the wavelength of these three lines to the mathematician Balmer. Balmer got the formula for these three lines, and that's why they are called Balmer series. They lie in the visible region of the electromagnetic spectrum. If the electron jumps to the third level, then we have got Paschen series. After this, all the series will be in the infrared region. So from here onwards, everything is infrared. Lyman, Balmer, Paschen. Next one is bracket. So jumping here, you have got the bracket series. Again in the infrared region. After bracket, we have got fund, or some people call it P fund. So this is the next series, right? And here we have got the last series, Humphrey. Okay, actually we can have infinite number of series. So this is the emission spectrum of hydrogen. Whenever electron goes to an excited state, it remains there only for 10 to the power minus 8 seconds, and then it jumps back. When it jumps back, it emits radiation having an energy equal to the energy difference between the levels. And this is of a particular wavelength. Jumping from 2 to 1 will give you some specific wavelength. And here we have got the series of lines we get: Lyman, Balmer, Paschen, bracket, P fund, Humphrey. Lyman lies in the UV region, Balmer in the visible region, and remaining lie in the infrared region. The formula for calculating these wavelengths was initially given by Balmer. That formula was modified by Rydberg, and that equation is 1 by lambda equal to R 1 by NF square minus 1 by Ni square. Right? Ni is the initial orbit, NF is the final orbit. Now some of you may always get confused with the formula which is first NF or Ni. One simple thing to remember, these are in alphabetical order. F comes before I in the alphabetical sequence. Okay, otherwise this has to be a positive quantity. That way also you can understand that this has to be a bigger number, this has to be a smaller number. So this is the formula for calculating wavelength in the emission spectrum of hydrogen. When you move to hydrogen like, we have to multiply this by Z square. R Z square 1 by NF square minus 1 by Ni square. This is for hydrogen like. So we get Z there. When you look at K alpha X-ray, this formula becomes R Z minus 1 square. This is for K alpha, right? And you jump to the first orbit from the second orbit. So here you get 1 by 1 square minus 1 by 2 square. From here you get Moseley's law. You multiply this by C, you get frequency. So C by lambda K alpha will become 3 by 4 RC Z minus 1 whole square. If you take square root, this is frequency of K alpha X-ray. So square root of frequency of K alpha is equal to root over 3 RC by 4 into Z minus 1. This is what is Moseley's law of characteristic X-ray spectrum. And this one led to the concept of atomic number, right? So all this started from the emission spectrum of hydrogen. In fact, Bohr model also started with the emission spectrum of hydrogen. And here we come to the concept of atomic number. So this formula we have to remember. Right now we are looking at this formula. 1 by lambda equal to R into 1 by NF square minus 1 by Ni square. If you multiply both sides by Hc, what do we get? Hc by lambda equal to RHc 1 by NF square minus 1 by Ni square. And this is nothing but energy difference delta E. So this is EI minus EF. And if you apply your brains a little bit, you realize that therefore E is equal to minus RHc by N square. Therefore what is RHc? RHc therefore is 13.6 electron volt. So this is important to remember and understand. Product of Rydberg's constant, Planck's constant and speed of light is 13.6 electron volt. And how we got this equation? If this is energy, but first put I here, so you get Ni here. Put F here, put F here. Then you do EI minus EF, you'll get this equation. Just think on that. Very, very easy. So important thing to remember in the emission spectrum of hydrogen is 1 by lambda is equal to R, Rydberg's constant, 1 by NF square minus 1 by Ni square. And Rydberg constant is having a value of 1.097 into 10 to the power 7 per meter. It is 1 by lambda, so per meter. And 1 by Rydberg's constant is something that is useful to remember, especially while solving problems. This is equal to 0.911 into 10 to the power minus 7 meter. Right? As simple as this.